exactly the meaning of this particular antenna here. I mean, how exactly the structural features are there here, and how exactly it is going to be operated here, and also the equations concerned with that particular antenna, and what are the advantages and applications and disadvantages concerned with the particular antenna we are going to study here. Only the loop antenna in this particular chapter we are going to see a little bit of in detail here, like radiation resistance for loop here, directivity of a loop here. Okay, loop in general here. We try to compare the small loop here with the short dipole here, which we have learned in the previous model here. That's we are going to learn in this particular module here. And all other types of antenna, like rectangular horn antenna you're going to learn, helical antenna you're going to learn, Yagi-Uda antenna you're going to learn, parabolic, log periodic. Okay, these are the 5 to 6 antennas. Okay, 5 to 6 antennas you're going to learn here, and the corresponding problems will also be there here. Remember, so what exam this particular model will be there is types of antenna, and the diagrams will be there, and only one or two derivations is there, like radiation resistance of a loop and directivity of a circular loop will be there here. Only two derivations are there here, and after that there are problems here on every antenna here. For every antenna there is a problem here. Even if you consider with the horn antenna, helical antenna, Yagi-Uda, parabolic, log periodic, okay, and rectangular, all the 6 antennas will be having problem here. Okay, that has been asked in previous examinations here. If you understand the parameters or whatever the labels are there here corresponding to the antenna here, whichever antenna is there, if you understand clearly, definitely you are going to solve the problem here. And one or two little bit of formula is there here, that formula you have to remember here. So if we do this one, it will be more easier to understand the whole model here. There is not much of a theoretical concepts to be remembered here, but yes, we have one particular antenna, its specification, its structure, its parameters, its application, its operations. This much you have to remember, and corresponding problem will be there. Every problem, every antenna will be having its own problem. That problem need to be solved here. Okay, so almost like 40% of problem, and 20% of theory, and 40% of all the structures and everything you have to go ahead here. Right. So with this one, we will begin with today's class here. What I'm going to cover is two antennas I'm going to cover here. One is rectangular horn antenna here. Okay, and another antenna which I'm going to cover is Yagi-Uda array here. These two antennas I'm going to cover today, and tomorrow I'm going to cover another 3 antennas. Okay, so today we'll cover this horn antenna and Yagi-Uda array here. Two antennas we are going to cover here. Okay, just a minute. Someone else. So we'll begin with this horn antenna here. So horn antenna, okay. So it is this is going to be the part 2 here. Remember, part 2 here. Part 1 is totally of loop antenna only here. Loop antenna, it's radiation resistance, directivity, general case, everything will be covered in the part first only. But only one antenna will be covered here. And then the second part here will be learning all these 5 antennas here. Okay. So horn antenna is this one here. So what is this horn antenna? Okay, this is regarded as a opened out to waveguide here. So usually why this particular antenna will be selected many a times is because of its what you can say that very high directivity here. Okay, you know the meaning of the directivity here, which you learned in the third module, second part here. So the greater directivity will be there. That's why many a times here this horn antenna would be utilized here. Okay, and also it is the one antenna which is having the larger aperture here. That is the front face here, right? So these are all the several types of horn antennas we could see in this particular figure here. Okay, in the left side you could see that we are having the antennas which are rectangular in shape here, and in the right side you can see it is in the circular type here. Okay, like here we are having the common type of antenna is this one here. Okay, exponentially tapered pyramid kind of an antenna. This is a very common type of horn antenna, which is we are going to study in the next page here. So this is what is at the throat here, and the waveguide. This is the waveguide here. and this is the aperture surface here, or you can say front face you can consider here. Okay, this is a very common type of an horn antenna which we are going to study in the further class here. Okay, this is one kind of an exponentially tapered kind of an horn antenna here, and this is one conical type here, and this is biconical here. The two sides we have a conical face here, that's called as a biconical here, and this is also a kind of an horn antenna here, which is E plane here. Okay, so this is E plane, sectoral E plane horn antenna here, and this is sectoral H plane horn antenna here. So these are the types of an horn antenna here, which we are having and we are going to study here. Normally, we are going to get a question in the examination like what is exactly the definition of an horn antenna here and types of antenna. Only once it has been asked in the previous exam question paper here. So what you have to do here is at this point you have to write the definition of the horn antenna and mention all these diagrams here. You have to draw correspondingly, like 6 to 8 marks will be asked in this particular first introduction itself only here. Now let us go ahead with the further topic here. So the further topic, what you can see here is the common type of an antenna which is been asked in the many examinations here, and corresponding derivations also is been asked here, and the problems are also asked here. So in this particular topic, that is horn antenna, which is of pyramid shape here, right? As we have gone through the first figure here, there you can see. So it is you can see here, this is the horn mouth here. Okay, so this is AE is there here, vertical, AH is horizontal here. Okay, these are the sides here, sides of the horn antenna here. Now if at all we have this cross-sectional view, then we can see here there is the length between the whatever the throttle and the end of the, what you can say, that horn mouth here, it is capital L here. Okay, so the whatever the mouth diameter is, that is considered as A here in this case here, total, and there is a small length called as a delta here, that is we have mentioned here. Now this thing exactly, and the angle that has been made in theta here. Okay, so now see here, you can see the two right angle triangles here. This is one here, and another one is like this here in the downside here. So we wanted to calculate the parameters concerned with this particular horn antenna here. Okay, so now how exactly we are going to calculate? From the figure we can see here is, suppose if I consider this particular half part here, upper half part you can consider here. So you can see this totally it is A here. If at all I consider the half here, it is A by 2 here, and here it is also, it is capital L here, and here it is L plus delta here. So using the right angle triangle here, we can write the cos theta by 2. Okay, cos theta by 2 is nothing but here whatever the L divided by L plus theta here. Hypotenuse is there, L plus delta here. And if you take the sin theta here, sin theta is nothing but here A by 2 divided by whatever the hypotenuse we are having here, opposite by hypotenuse here. Then tan theta is nothing but here, you know this one here, sin theta by 2 divided by cos theta by 2 here. So we have A divided by 2 L here. So these are the three things you are going to get here from the figure here: cos theta by 2 and sin theta by 2 and tan theta by 2. So what is exactly theta here? Theta is nothing but here flare angle, it is called as here. So flare angle that is concerned with the E plane is theta E here, and for H plane it is theta H, which will be always in terms of the degrees here, right? Okay, now aperture is there. A is nothing but here aperture here. Aperture in the E plane, this is this side here, AE, and AH in the H plane here, which will be always in terms of meters here. L is nothing but here horn length, and how much is the length of the horn here? Okay, from the throttle towards the plane surface of the mouth of the horn here, how much is the length here? That is represented by capital L here. Delta is nothing but here path length difference, that you can see here above. Okay, path length difference here. Now there is something called as a principle of equality here. So from the principle of equality, what you can say here is that Okay. uh, this particular principle of equality of the path length is applicable to our horn design here. Okay, so where what we can see here is there is a deviation of the phase here. Okay, when we consider the wave at the center here or at the side walls here, there is a phase difference here. Okay, or you can say that phase may deviate here according to the length here. So what we are going to consider here is this phase deviation is very less here, very less, very less when we try to compare the length of the whatever the side is there, that is L plus delta, or whatever the horn length is there here. Okay, so now, from the geometry, what we can see here is that we, we have L is equal to A square divided by whatever the 8 delta is there here, right? So if at all we wanted to find out regarding the length here, length could be find out whatever the aperture is there, A into A divided by whatever the constant term 8 into whatever the path length difference is there here. Delta is nothing but here path length difference. If at all we have a path length difference, and if at all we have the value of the A here, we are able to find the horn length here. Okay, that is what is the equation number 1 here. Suppose if at all we wanted to find the flare angle here, that is nothing but here theta, the how much angle is there between the two sides of the horn here, horn antenna. So that is nothing but flare angle here. That could be found out with the help of again the same term, that is the A and also the path length difference. If at all we have these two things here, and we are able to find out the theta also here. Okay, and if at all we have path length difference also, we are able to find out the theta here, that is flare angle here. Okay, now there are separate path length difference here, and suppose if you are considering the horn antenna in the E plane here. Okay, okay, that is I think you are able to understand regarding this E plane and H plane here, right? So E plane, sectoral E plane and sectoral H plane, in the first page we have learned, no? That is types of antennas there will be having sectoral H plane and sectoral E plane here. If at all I consider a sectoral H plane, if at all I consider the sectoral E plane here, how much would be the path length difference that we are mentioning here? If at all I consider the E plane of the horn antenna, then delta is equal to, it should be 0.25 lambda, or it should be less than that also here. It should be less than, then only it will be going to operating as a E plane here, E plane. And if at all we have a H plane here, then the delta will be, okay, can be larger or greater than the 0.4 lambda here. Okay, so now there are some dimensions here that has been given here. Optimum horn dimensions, you can call it as standard values for standard values to get the path length difference and the length of an horn antenna here. That is delta naught is equal to L divided by cos theta by 2 minus of L here. Okay, and if at all we wanted to calculate the length here, the same thing, if at all we can utilize the same equation and get the length here. There is optimum length and optimum delta here, that is path length difference here. Okay, so we are going to get from the equation 3 and equation 4 regarding the optimum path length difference and the optimum length here. If at all the problems have been asked in the examinations here, so you have, if at all you wanted to find the optimum length, means you have to use this particular formula, L is equal to delta naught cos theta by 2 1 minus cos theta by 2 here. If at all there is a mentioning of the optimum length here, you have to find the optimum length of the horn antenna or optimum path length difference of the horn antenna, means you have to utilize this particular function. If they are not going to mention anything here, if they say just path length difference, means you can utilize delta here. Delta is, you can utilize equation number 1 here. Delta is equal to how much? Delta is equal to A square divided by 8 into L here. Okay, or if they ask you to calculate the capital L here, just the length of the horn antenna, means L is equal to A square divided by 8 delta here. If they mention optimum, means you have to utilize this equation number 3 and 4 here. Okay, now the very whichever the antenna is there here, you have to have the directivity here, right? So directivity or gain of an horn antenna can be expressed in terms of the effective aperture. Here we try to express whatever the directivity is there regarding the horn antenna in terms of the aperture here. So you know this particular formula here, we have derived these equations in the previous classes here. The third model we are having a delta is d is equal to capital D is equal to 4 pi AE divided by lambda square here. I think you know this AE. A is nothing but your effective aperture, which will be meter square here. Okay, if at all further further modification or further equation you consider here, 4 pi aperture efficiency AP here, right? So you know this one here. Okay, A is equal to, you can write aperture efficiency into the physical aperture here. Okay, lambda is nothing but here again a wavelength here. Now if at all we consider the rectangular horn antenna as AE into AH here, or you can also consider here, because it is a rectangular horn antenna, H height into width, you can also consider it physically. If you consider, sorry, the AP is equal to H into W here, area of the horn mouth opening here, that is nothing but aperture here. Okay, so H into W here, this one, H into H is nothing but your height here, that is AE here. W is nothing but your width of this particular horn antenna here, horn antenna mouth here. Okay, so that you can place here H into W here. Okay, if at all we consider that the AE and AH are at least 1 lambda, then what over the aperture efficiency here? Aperture efficiency is given by 0.6 here. If at all we consider the height and width of the horn antenna or rectangular horn antenna has 1 lambda here. Okay, so if at all we consider aperture efficiency as 0.6 here, if at all we multiply this 0.6 into 4 pi here, so what is going to have here? 7.5 AP divided by lambda square here. Again, if at all we wanted to have this particular directivity here, if at all we have physical aperture and the lambda here, definitely we are going to get the directivity of the particular rectangular horn antenna here. And this could also be derived in terms of what you can say, I mean, not derived here, we can get to the answer in terms of the dB here, decibels here. So just include 10 log here, 10 log 7.5 AP into divided by lambda square. Then this particular thing G is equal to gain is there, no? Gain is nothing but we can write 4.5 into H into W divided by lambda square here. This is the directivity here. If at all you wanted to find the directivity of the rectangular horn antenna, you utilize this particular formula. Okay, if at all we wanted to find the gain here, G is equal to 4.5 into H into W divided by lambda square here. Okay, so this is how we are going to get the directivity and gain here. And lastly here, there are beam width within first null and the half power beam width is there here. Directly you can write this particular formula here, that is 115 divided by AEH here. Okay, AE lambda here, sorry, AE lambda, and 172 divided by A H lambda here, suffix here, remember. Okay, and again the half power means that is almost divided by 2 will be there here, 56 divided by AEH here, or 56 into lambda divided by H here. Okay, in the same way, you already know that AE is nothing but what here? AE is nothing but here height here. A suffix E is nothing but here this one. A suffix E is nothing but here height here. A suffix H is nothing but here width here. That's why AH will be replaced by W, and AH lambda is nothing but here lambda divided by AH here. Remember, lambda divided by AH is nothing but here AH lambda here. So that's why lambda by W we are writing here. In the same way here also, AEH is AE lambda is nothing but here AE divided by lambda here. Okay, so AE is nothing but here H is a lambda you can take in the numerator here. That's a 56 lambda divided by H and 67 divided by 67 into lambda divided by W here. Okay, so this much is the regarding the rectangular horn antenna here. As I mentioned, I'll just going to revise once here. You have to remember this particular definition here, horn antenna. Okay, and then the types of horn antenna here. Okay, okay. One more thing you just remember, it will be having the uniform phase here, as it is having the larger aperture here. Okay, and hence the greater directivity will be there. These are the types of horn antenna here, and this is what the basics which I have discussed just now. Okay, now whenever there has been a question regarding the rectangular horn antenna explanation, some people I think have confused with one of the question that has been there in the assignment here. So what you have to write here, this answer you have to write here. Rectangular horn antenna means you have to start writing from this particular page number 3 here. Okay, so rectangular horn antenna, if anybody asks you a question here, you have to draw this particular diagram, cross sectional, mention the labels here L, delta and A here, and start deriving the getting this particular that is cos theta by 2 from this geometry here. It is you have to get the value of A, L, delta here, or you have to mention A, L, delta equations here. Okay. So then and rectangle horn antenna specification you can consider. If at all you wanted to find the directivity, utilize this particular formula. Gain, you can utilize this particular formula here, 4.5 into h into w divided by lambda square. Or if at all there have been the question a problem here to get the beam width between first null, directly you can utilize this particular formula, 115 into lambda divided by h here. That you can beam width between first null. If at all half is there, 56 into lambda divided by h here. Okay, in the same way you can go ahead with the h plane also here.